Hello and welcome back. It occurred to me that I totally forgot to do the astronomy picture of the day today. I know you're all craving your astronomy pictures of the day, going through withdrawal. Although, let's be fair, you could have been looking at it all along. Here is today's astronomy picture of the day. I'm filming this on Monday, April 27th. This is the moon Enceladus, one of Saturn's moons. This is a fascinating moon. You can see it's got all kinds of cool craters here. It's got some weird blue tiger stripes that seem to be fairly fresh. And this is one of the most exciting objects in the solar system because we think, we have reason to believe, we're very confident that below the surface of Enceladus, which you can see is very white, this is actually, we believe, a snow kind of on a thick layer of ice. But below that ice, we're pretty sure that there exists a liquid ocean. And we have pretty substantial evidence to back that up, including the fact that Enceladus is an active geological, solar system body. In other words, there are geysers and things that regularly pop up from the surface, which are spraying, we think, liquid water into space. Well, it's not liquid for long, but that's cool. What makes it even cooler is it is a possible place in the solar system other than Earth where life could exist and evolve. We know that there are regions on Earth that never get sunlight, like at the bottom of the ocean, where marine life is fed by geothermal vents, chemicals and heat bubbling up from vents below. And entire ecosystems can thrive at the bottom of the ocean where no light ever reaches. It is possible that those kinds of things have happened in the subsurface oceans on Enceladus. There could be life on this moon right now. And maybe there's another moon in the solar system called Europa, which is a moon of Jupiter, which has a very similar kind of structure, liquid ocean below an ice layer. It's possible in your lifetime that we will send a probe to one of these two places. It will dig down below the surface of the ice, swim around, and look for life. Could be that we find it in your lifetime. That would be pretty cool. Okay, let's get back to something else that's very cool, which is the Hubble law. There we go. We left off doing some calculations on the Hubble law. We've seen kind of how it works. Here is the Hubble law, again, a graph of the Hubble law. You can see, again, recessional velocity, how fast galaxies are moving away from us, proportional to how far they are away from us. So, what are the implications? They are pretty amazing and pretty intense. So let's think about one of these galaxies here. Let's say, I don't know, this one here at 5 megaparsecs away. It's moving away from us at a little more than 3,000 kilometers per second. So you could reverse the clock, right? This galaxy is moving away from us at a certain velocity and it's a certain speed away from us. You could reverse the clock, right? And say, well, if it's been traveling away from us at that speed and it's that far away, how long ago was it before that galaxy was where we are? Right? Velocity equals distance times time. How long, if it started where we are, how long has it taken to get there, given how far away it is now and how fast it's moving? And you get some number. The interesting thing is, let's take this galaxy out here. It's twice as far away. It's 10 megaparsecs away, but it's moving away from us twice as fast, a little more than 6,000 kilometers per second. What number are you going to get for this value, for this galaxy? For, again, how long it's taken to get there, given its current rate of speed. I'll give you a hint. It's exactly the same as this one. This galaxy is twice as far away, but it's moving away from us twice as fast. This galaxy out here is moving away from us 3 times. Oops. Sorry. Press the wrong button. This galaxy out here is moving away from us 3 times as fast. Well, actually, this is kind of a log scale. This one's moving 3 times as fast as this one. and it's moving away from us, guess what? 3 times as fast. All of these galaxies, if you do that chart, the math, for how long it's taken them to get there, given their present velocity and rate of and distance from us, you get exactly the same time. So if you rewind the clock, there was a time in the past when all of those galaxies are where we are right now at the same time. That's what we call the beginning of the universe. We think that the universe began very hot and very dense, and this is one of the major reasons we think why. It had to be in the very past, very distant past, all of these galaxies were closer to us, and it had to be in the distant past, all of those galaxies are basically where we are now. So that's weird. That tells you the age of the universe. In fact, the Hubble constant, the slope of this line, tells you the age of the universe. Any galaxy, if you know how far away it is, you know how fast it's moving away from us, you can calculate the age of the universe just by the slope of this line. Now, the Hubble constant is the slope of this line, and let's think about this carefully. If the universe is young, these galaxies all would have had to get to this distance fast, and so you'd need a steep slope, right? The steeper the slope, let's think about this. The steeper the slope, the closer a galaxy is going to be to us at a given velocity. And so the shorter amount of time it would have taken for that galaxy to get to us. And so the age of the universe, velocity equals distance divided by time. The other way to think about this is velocity equals distance divided by time. Well, let's actually do this. Let's not talk about it. Let's actually show it. Yes, it still takes me forever to transform between them. Okay, so we know that velocity equals distance divided by time. This is what we're going to use to calculate how long it has taken. We need to solve this for time, really. But we also know that, well, let's solve this for time, sure. Let's multiply both sides by t. The t's go way over here. Divide both sides by v. We get time equals distance divided by velocity. Great. Well, we also know that distance and velocity are related by the Hubble constant. Remember that? D equals h naught times v. That's the Hubble law. So this is going to be pretty cool. Are you ready for this? What is... Dang, I got that wrong. It's actually exactly the opposite. Velocity equals h naught times d. That is the Hubble constant. Haha, I knew I got something wrong. So what is d over v? We want to know what d over v is so we can relate time to the Hubble constant. Well, d over v, divide both sides by v. They go way over here. We also need to divide both sides by the Hubble constant. D over v in the Hubble law is equal to 1 over h naught. So t, which is d over v, is also 1 over the Hubble constant. If you want to know how old the universe is, all you have to do is take the inverse of the Hubble constant. Well, that's pretty cool. In fact, I did that right because it's on the next slide. The age of the universe is about 1 divided by the Hubble constant. What do these squiggles mean? For those of you who are math junkies, if it's equal to, you get a good equal sign. If it's a squiggle equal sign, it means it's about equal to, roughly equal to, not exactly equal to. Well, that's interesting. Why isn't this an exact formula? What assumption are we making here that maybe isn't valid? I'll give you a hint. It goes back to this diagram. The assumption that we've made in assuming that velocity equals distance divided by time is that these galaxies have been moving at that velocity for the entire time they've been moving away from us. And that isn't necessarily the case. But this is still going to give us a decent handle on what we expect the age of the universe to be. So let's do it. What is the age of the universe? This is exciting. We now know enough to actually calculate the true age of the universe just given a couple of numbers. Given one number, the Hubble law, the Hubble constant. So, go back to my whiteboard. What is the Hubble, what is the age of the universe? Well, we know that T equals 1 over H naught. We know that H naught is 72, it's right over here, ish, kilometers per second per megaparsec. Weird number and weird units. So this is 1 over 72 kilometers per second per megaparsec. Now this gets weird and hard, so bear with me. We need to take 1 over 72, so we need to take the inverse of 72. 1 over 72, the number, is something like 0.0139. Now what are the units on this number? We've taken the inverse of the number, we also have to take the inverse of the units. So this number, instead of being kilometers per second per megaparsec, is the inverse of that unit, which is just flip it over, seconds times megaparsecs divided by kilometers. Great, that's our time, except the units are all messed up. That's not really a unit of time, except it is. Seconds is where we want it to be on top. That gives us a time unit. And then we've got a megaparsec divided by kilometer. Well, those are 2 units of distance. They should be able to cancel out. They don't, but they can if we do things right. And so these 2 can go away if we're careful, and this can be transformed into something that is just a unit of time. And that's really what we want to do here. So what do we need to do? We need to multiply this by a number which has kilometers on top and megaparsecs on the bottom. In other words, we need to know how many kilometers there are in a megaparsec. That's going to be our goal now. You could just look this up on Google if you want to, but let's think about it a little bit. 1 parsec is 3.09 times 10 to the 16 meters. We know that there's 10 to the 3 kilometers in a meter, so there's going to be fewer kilometers in a parsec than there are in a meter, than there are meters in a parsec. Fewer by a factor of 1,000, which is 10 to the 3. This is 3.09 times 10 to the 13 kilometers, 1 parsec. A megaparsec is a million parsecs. So you just need to add 6, multiply this number by a million by 10 to the 6, which means adding 6 to the exponent. 3.09 times 10 to the 19 kilometers. Okay, and that's the number we need over here to multiply. That's the number of kilometers in a megaparsec. I can put 3.09 times 10 to the 16 on top. In fact, let me do it. 3.09, I said 16, I meant 19. Times 10 to the 19 kilometers divided by 1 megaparsec. Great. So I take my 0.0139 seconds megaparsecs per kilometer, multiply by 3.09 times 10 to the 19 kilometers per megaparsec, and I get kilometers canceling out, I get megaparsecs canceling out. I'm going to get a number which is about 4.3 times 10 to the 17. And what are the units on that number? Well, all of these units have gone away except for seconds. And that's my unit. Great. So we calculated the age of the universe is about 4.3 times 10 to the 17 seconds. Well, that's a gigantic number. And seconds probably isn't the unit that we want to use to express this number anyway. We're more interested in years. So I can take this number and do my usual seconds to years calculation. We know that there are, this is the opposite of the seconds calculation we've done before. We need minutes on top and seconds on the bottom. So we know in 1 minute, there's 60 seconds. We know that in 1 hour, there are 60 minutes. We know that in 1 day, there are 24 hours. And we know that in 1 year, there are 365 days. So we take this number, we divide it by 60, we divide it by 60, we divide it by 24, we divide it by 365. Days go away, hours go away, minutes go away, seconds go away, and I'm left with years. And at the end of doing all of that, or just plug it into Google, you're never going to have a point the rest of the semester where you're not going to be able to plug things into Google. But here I am doing things by hand anyway. Anyway, you get a number that is 1.36 times 10 to the 10. That says 16, it should say 10. Sometimes I can't write very well. Years. There it is. We just calculated a billion is 10 to the 9. So this is 13.6 billion years. All you need to know is the Hubble constant. And if you know the Hubble constant, you can calculate the age of the universe. In fact, that's very close to the number you'll get if you look it up in a textbook or Wikipedia or wherever it is you go to get your information. So that's exciting. We just calculated the age of the universe just by knowing a single number. There we go. What is the age of the universe? We did it. Okay, so I'm going to stop there because this is another very cool and important thought question. I want to pose it to you first, and then we'll answer it in the next video. Is the Milky Way at the center of the universe? It sure seems that way, right? We certainly seem to be at rest, we being the sun and all the stars in the Milky Way galaxy, and every single galaxy in the universe seems to be moving away from us. Let me just draw what that looks like real quick, because this is an important thing to visualize. Okay, so here we are in the center of the whiteboard. Maybe it's the center of the universe. And we've got a bunch of galaxies around us, right? Some of them are nearby, some of them are far away, some of them are in this direction, some of them are that direction. All of them seem to be moving away from us. Every single one of them. And not only that, the further they are away from us, the faster they seem to be moving. So, it certainly looks like we're the center of the universe, doesn't it? Are we though? Well, stay tuned. I will answer that question in the next